So we're going to talk about problem solving. So George Polya's problem solving method tells us that we need to understand the problem, read, consider everything, and identify the question. Then we need to devise a plan. That means to choose a strategy that makes sense. The third one is to carry out your plan, process through your strategy to a solution. And then the fourth would be to check your answer. Does the answer fit the problem's condition, or does the answer make sense? Well, problem-solving strategies that we could use would be to draw a diagram. That could be a flow chart, a tree diagram, a graphic representation, a model, a floor plan, a Venn diagram, or an array. So we're going to work some problems that we're going to use some of these ideas of things that we could do to figure out what a question's asking and how we can solve the problem. So the first example we're going to look at are some students who went off camping. So we're going to call them 4 campers. And we're going to visualize a condition in a word problem. So we've got 4 campers. We've got Alice, Ben, Christy, and David. They have just arrived at the Seeds of Peace Camp in Maine for an orientation session. Each will shake hands with all of the others. Draw a picture to illustrate the situation and determine the number of handshakes. All right, so we've got 4 campers, Alice, Ben, Christy, and David. So we're going to set up a diagram that will show us what this looks like. So I'm going to draw 4 dots in a square because that'll be the easiest shape to make with this. So we had Alice, and we have Ben, and we have Christy, and we have David. You could write all the names out, but in this case I'm just going to do their initials. And they need to shake hands. Well, I know that Alice would shake hands with Ben, she would shake hands with David, and she would shake hands with Christy. Now Ben is already shaking hands with Alice, but he needs to shake hands with David and Christy. Now David's already shaking hands with Ben, he's already shaken hands with Alice, but he also needs to shake hands with Christy. And we can see that Christy is shaking hands with everybody. So that's a way to draw all of the possibilities of shaking hands. But how many possibilities are there? Well, let's just number them. So this is 1 handshake. This is 2. This is 3. This would be 4. But we have 2 more. We have this one and we have this one. So we have 6 ways they can shake hands. And that tells us that 6 handshakes occurred. All right, so let's go look at our second problem. So here we're going to draw a tree diagram. Tony is selecting his courses for the next semester. Because he works afternoons and also commutes, he must schedule classes that meet only on Monday, Wednesday, and Friday in the mornings, and has decided on the following possibilities. There's a math class at 9, 11, and 12, English at 9 or 12, sociology at 10, 11, or 12, art history at 9, 10, or 11, and we need to determine the possible ways that Tony can schedule these classes. So this will be example 2, and a tree diagram looks like the branches on a tree. And you can start from a side or you can start from the top. It doesn't matter. Because we're doing a schedule, I'm just going to start from the side. It doesn't matter which way you go. And we're going to call this Tony's schedule. We got to have a starting point. Now, The first one it tells us is that he has math as a choice for 9, 11, or 12. So that tells us we have 3 choices, so we have to have 3 branches that come off his schedule. So here's 1 branch, 2 branches, and 3 branches. And we will then state that this is the math branch. We've got 1 here, 1 here, and we'll try and keep this in alignment. This is at 9, 11, and 12. All right, next it says English is at 9 or 12. So that tells me that I have to go 9 or 12. Now, if I already have a math class at 9, I can't do an English at 9. So on the first branch, we will only have 1 that comes off. This will be English. And this can only happen at 12 because we already have the 9 o'clock math class. But at 11, I can have 2 branches that occur. Well, let's try to keep it in line. I can take the 9 or the 12 for English. And at 12, we can only do the 9 o'clock. Because you can't have 2 classes at the same time. All right, so we've got math and English. The next one that happens is sociology. It's at 10, 11, or 12. So we're going to do sociology next. And it can be at 10, 11, or 12. Well, the 12 won't work, but we can do 10. And we can do 11. Now, for this one here, we already have, remember, our choices are 10, 11, or 12. This one already has 11, so we can do 10 or 12. So 10 or 12. At this one, we can only do 10 because we already have an 11, we already have a 12. So this one can only do the 10 o'clock. On the one down here, we already have a 12, so we can do the 10 or the 11. All right, so are you following so far? I hope so. All right, last schedule class is art history, 9, 10, or 11. So we're going to have art history, 9, 10, or 11. So we already have a 9, we already have a 10, so art history for this one, this branch can only be at 11. So 9, 10, or 11, we have 9, we have 11, so this branch can only get the 10. 9, 10, or 11, oh, this one here is not possible. All right, 9, 10, or 11. So we have 9, we have 11. So this one could still have the one at 10. 9, 10, or 11, we have the 10, 11. We need the 9. If we go down here, we have 9, 10. Well, that tells us that we could do the 11 o'clock here, 9, 11. That tells us we can do the 10 o'clock. So you just have to pay attention and follow the entire branch. So here we can see that none of our times on each branch repeat. We can follow it along and we can see that if those branches were complete, we have a class at 9, 10, 11, and 12 on each branch, except for the one that was not possible. So we have 1, 2, 3, 4, 5, 6 ways he can schedule his classes. Okay, that's using a tree diagram. All right, so let's look at another example, and this one will be a Venn diagram. So if we look at example 3, assume that one group of students who are interested in physical fitness is taking Zumba classes and another is taking Pilates. Choose good names for these groups and represent the situation with a diagram. All right, so first of all, we have to remember what a Venn diagram looks like. So we're looking at the universal set, and we're looking at two circles here. So we can call one Zumba and one Pilates. Now, we're assuming that one group of students are interested in physical fitness, is taking Zumba, another is taking Pilates. Choose good names for the groups. Well, there's some different options that are happening here. So I'm just going to use the letter T. We would have some that are out here, some that are out here, or in there, some are here, and some are there. So in a Venn diagram, if we have these 4 categories, and we're looking at those 4 categories, what could we say represent the different categories? So if we're looking at T1, what does T1 represent? What would be the group of students that we could call T1? Because these are our Zumbas and this is our Pilates, so T1 would represent, these would be, because we're looking at a group of students, this would be students not taking Zumba or Pilates. That means they're not in the Zumba class, they're not in the Pilates class. They're just outside of it. They might still be interested in exercising or in physical fitness, but they are not taking Zumba or Pilates. Maybe they are actually doing something else. Maybe they're just walking, maybe they're jogging. Doesn't matter. We're just looking at Zumba and Pilates. All right, the second group, what would they represent? Well, they're only in the Zumba group, so they would be students taking Zumba and not, or but not, Pilates. I wouldn't say they're only taking Zumba because they could be doing other things. We're just looking at them in comparison to Zumba and Pilates. So we would just say they're taking this one but not that one. All right, what about the third group? T3 would be people who are in the Zumba group and in the Pilates group. So what would they represent? This would be students taking Zumba and Pilates. And then T4, they are only in the Pilates group. So this would be students taking Pilates but not Zumba. So they're only taking the one group. They're not taking, or just taking the Pilates and not the rest. All right, let's go look at another example. So example 4, we're looking at listing options. So Nick is considering which optional features to include with his new smartphone. He has narrowed it down to 3 choices: quick charging battery, multiple windows, and high resolution camera lens. Depending on price, he will decide how many of these options he can afford and how many ways can he make his decision. All right, so this one we're going to do a list. So the 3 options we have are the battery choice, the windows choice, and the camera choice. We're not going to put all the adjectives, just because that can make it a little bit more cumbersome to write. So this would be example 4. So for example 4, we're looking at battery, windows, and camera. I'm going to make a chart here. All right, so here's the way we're going to work this. Is first of all, what are the choices he has? For those choices, because of cost, remember, so it's all depending on the cost. The first thing he could do is choose none of the options because it's too expensive for the particular. I mean, it's all going to come with a battery. It could come with windows, but not multiple windows. And it'll come with a camera, but maybe not a high resolution camera. So remember, these are particular things because they're all going to have those pieces. So if we're choosing none, that means this would be a no, and a no. So that would be choosing none. There's an option where he can't choose any of the things he wants because he can't afford them. Next thing we're going to do is look at choose one. So he's going to choose one option. That means this one would be yes, but these two would be no. Then we would have this one is yes, and these two would be no. And then we could say yes to the camera, and these two options would be no. So that would be choosing one option, depending on our cost, is all it depends on. Okay, the next one would be, let's choose 2. So that means we have a yes, but a no, a yes and a yes here, and a no, or we can have yes, and there would be a no here. So there's going to be those options where you choose 2. The last one would be if we find a good deal, and it's in his price range, he could choose 3. So that means he would get to have all of the options he's looking for, and that would be that one. So how many possibilities are there? Well, let's count how many we ended up with. We had 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 ways Nick can make his decision. Now, are they all the decision he wants? No, he's not going to want all of the options because he doesn't want this option for sure. He really wants this option. He wants to choose that one. But there are 8 ways he can make it. All right. Looking at example 5, we are finding patterns in Pascal's triangle. So these are the rows going across here. And we are looking at, there's a pattern that happens here. So we're going to kind of look at this, and I'm going to read some stuff. So notice how each number is the sum of the 2 numbers immediately above it. So if we look at this 4, the 2 numbers immediately above it add to be 4. Here we have 6 plus 4, well that would equal 10. And you could see if you looked at this 2, there's 2 ones above it, so that means we have 1 plus 1 is 2. 2 plus 1 is 3. So it works throughout. Suppose we want to find the total of all the numbers that will be in the 9th row of the diagram. If we look at the pattern in row 3, which is this row right here, we have 1, 3, 3, 1 in the Pascal's triangle. It's similar in the form of example 4. There was 1 way to choose no options, 3 ways to choose 1 option, 3 ways to choose 2 options, and 1 way to choose all 3 options. So let's go back and look at what we had here. So this is what we're talking about, this example here. We had 1 option, we have 3 options, we have 3 options, and we have 1 option. So that's that 3rd row in the Pascal triangle. All right. So it's interesting how the same pattern in math can occur in similarly different situations, seemingly different. So we're looking at, here's a Pascal triangle, and here's this. But even though they're different situations, they're getting the same pattern. All right, so we want to look at the 9th row. So let's see if we can find a pattern. So this will be example 5. So if we're looking at our rows, let's see what happens. So we're going to look at the row and let's look at the total. Because we're looking, our question stated, suppose that we want to find the total of all the numbers that will be in the 9th row of this diagram. So let's see if we can find a pattern that occurs. So we had row 0, and then we'll have row 1, row 2, row 3, row 4, row 5, 6, 7, 8, and 9. So in row 0, the sum of the numbers, oops, so sorry. Not good when your glasses fall off. So row 0, we have a sum of 1. So we'll write a 1. In row 1, we have a sum of 2. 1 plus 1 is 2. In row 2, we have 1 plus 2 is 3 plus 1 is 4. In row 3, we have 1 plus 3 is 4 plus 3 is 7 plus 1 is 8. In row 4, we have 1 plus 4 is 5, plus 6 is 11, plus 4 would be 15, plus 1 would be 16. In row 5, we have 1 plus 5 is 6, plus 10 would be 16, plus 10 would be 26, plus 5 would be 31, plus 1 would be 32. Now we don't have rows 6, 7, 8, or 9 written out, but what do we think is happening? What do we see that is occurring at this point? So, well, we can look at this and go, well, we've got 1, 2, 4, 8, 6, 32. What's the pattern that's happening here? Well, if I multiply 1 times 2, I get 2. 2 times 2 would be 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So 32 times 2 would be 64. 64 times 2 would be 128. 128 times 2 would be 256. And 256 times 2 would be 512. So this would be our answer. The total, or the sum of our 9th row of all our digits would be 512. Okay? Alrighty, so our next example will be example 6. And on example 6, we are looking at what we call guess and check. So the local history society wants to preserve 2 buildings. The total age of the buildings is 321 years. If one building is twice as old as the other, what are the ages of the 2 buildings? Alrighty, so let's look at example 6. So we have 2 buildings. So I'm just going to say we have building 1 and building 2. And that will equal our total. So if we add the 2 ages of the buildings, we have a total. And they want to preserve those. Now we know that one is twice as old as the other one. And we need to get to a total of 321. That's what they told us. It totals of 321 years. So whatever number we pick for B, we have to have twice that B1, the building, first building, the second building has to be twice that. So if I know I've got to get to 300, so let's go big. If I pick 100 for this one, for building 1, the second building has to be twice that. So 2 times 100 would be 200, and that gets us 300. Well, that's not quite 321. So let's add 5 years to this one, just for number's sake, like easy numbers. So 105, well, twice that would be 210. If I add that, I get 315. Not quite there. I need to get to 321. So I don't want to go up 5 more because the difference is only 6 between there. There's a difference of 6 more. So let's add 2 to this. So we'd have 107. Twice that would be 214. There is our 321. And this right here is the number we're looking for. So one building is 107 years, and this one is 214 years. So you're, again, using your logic skills to figure this out, but it's also a way for you to learn how problem solving. So, and you can see this in many instances in your homework. So, all right, let's go to number 7. On number 7, we have an algebraic statement that is always true. Find an example to illustrate that the statement is true. So we are given this equation here. X plus y squared equals x squared plus 2xy plus y squared. So this will be example 7. So we have x plus y quantity squared is equal to x squared plus 2xy plus y squared. So what we need to do is find an example to illustrate that the statement is true. So we need to pick an x and we need to pick a y. So let's go x is equal to 2 and y is equal to 4. Let's see how that works. So we've got 2 plus 4 squared. So we're looking at plugging in just the values for the x and the y. So x again is 2 squared, plus we have 2 times our x, which is 2, plus or times our y, which would be 4, plus our y squared. So 2 plus 4 would be 6. We're now squaring 6. 2 squared is 4. 2 times 2 is 4. Times 4 is 16. Plus 4 squared, that's 4 times 4, which is 16. 6 squared is 36. 4 plus 16 would be 20. 20 plus 16 would be 36. Oh, 36 is equal to 36. This is true. This is a true statement. Sweet. All right. And this will be true no matter what you choose because it's always true. And it comes from the fact that if you remember your algebra skills, just to help you understand a little further, if we take x plus y squared, remember, that's this first part, that is x plus y times x plus y. And if we FOILed that out, which we don't do in this class, but if we did, we'd end up with the x squared plus 2xy plus y squared. This will be true no matter what numbers you choose, okay? It's always going to be true. All right, let's look at example 8. So in example 8, we're looking at counterexamples to false algebra statements. Although the following two statements are false, those who are not secure in working with algebra often believe them to be true. Provide a counterexample for each statement. So a counterexample is where we're going to pick two numbers and prove it's not true. So the first one is part A. And part A says that we have x plus y squared equal to x squared plus y squared. And I see this a lot in my algebra classes. They're going to square x and they're going to square y, but we already know from the previous example, x plus y squared actually will equal this. This is true, this is not. So again, we're just picking a counterexample. So a counterexample is just a fancy way of saying pick something that shows this isn't true. So let's pick x is equal to 5 and y is equal to 7. All right, so let's plug this in. We have x plus y, so 5 plus 7 quantity squared is equal to 5 squared plus 7 squared. Well, 5 plus 7 is 12. Remember, we always got to follow those order of operations. 5 squared, that's 5 times 5 is 25. 7 squared is 7 times 7, which is 49. Well, 12 squared, that's 12 times 12 is 144. If I add 25 plus 49, that will get me 74. Oh, 144 does not equal 74, so this is false. That's all you got to do. That's a counterexample. It proves it's not a true statement. All right, let's look at example, or part B. So part B gives us the square root of x plus y, let's angle that out just a little more, is equal to the square root of x plus the square root of y. All right, on this one, I want to choose things that are perfect squares. That means it's something times itself, kind of like this 25 and 49. Because if we don't choose that, it's hard to take the square root. I want whole numbers when these come out of here. So let's choose x is equal to 81 and y is equal to 25, because then I can easily take the square root of those. Alrighty, so over here we will have the square root of 81 plus 25 is equal to the square root of 81 plus the square root of 25. Well, 81 plus 25, that gets me the square root of 106. Square root of 81 is 9. Square root of 25 is 5. So the square root of 106, when I put that in the calculator, I'm going to get 10.3, and 9 plus 5 is 14. Well, 14 does not equal 10.3, so this is a false statement. So remember that anytime you're looking at saying if it's true or false, if the numbers equal each other, so if 36 equal to 36, that's true. If they don't have the same number, that tells us it is false. Or we need to double check our math because maybe we made a oopsie in our math. Okay? Alrighty. So let's go look at our next problem. And our next problem will be example 9. So for example 9, we're going to reversing the order of operations can change the result of mathematical computations. So if we look at example 9, we are looking at x plus y squared is equal to x squared plus y squared. So we're looking at that one again. So we're just going to kind of look at what's happening with those. So on the left side, we're looking at the wording of it. What does that mean? So if we look at the left side, what do we do first? As far as order of operations, we are going to add and then square. So we will add x plus y, and then we will square the sum. So after we add them, we'll square the sum. On the right side, we have x squared plus y squared. So on the right side, we square x and y, then add the squares. So, notice the difference of what's really happening is basically what we're looking at. We add them, then square them. Here we square them, then add them. So that's where you're looking at it. You're looking at the difference between them. So on the first one, we're looking at first add them, and then add, then square. And on the other one, we're going to first square, then add. So it's basically opposite. Add, then square, square, then add. So it's a way of looking at what is the process, and reversing them can actually change. Reversing the adding and the squaring changes the mathematical computations on there. So it's just looking at the process of which things can happen. So this is some ways on how to problem solve. Remember, that's what we're looking at, is different ways we can look at problems and how we can solve them.